Hey, so yeah, I put up a warm up, um, and yeah, I guess we can. Let's say we resume. Oops, at 5:15. Actually, let's give it a little bit longer. I don't know, 5:17 or something, and yeah, we'll take it from there. All right, so let's go over this. So let's see. So say f of x equals x, right? Then by definition, Bnf of x is the sum of f of k over n, and choose k, x to the k, 1 minus x to the n minus k, k equals 0 to n, which, so this is just k over n, right? So this is the sum, k equals 0 to n, k over n, and choose k, x to the k, 1 minus x to the n minus k. And then this is 1 over n times the sum of k, and choose k, x to the k, 1 minus x to the n minus k, from k equals 0 to n. And then basically, so what I was saying in the hint was, if you look at the proof of lemma 27.2, they have some formulas for sums of this type, basically, where, so like this one, they actually explicitly, they just compute this one directly. So this is nx from the proof of 27.2. So if you want, I mean, obviously you could replicate their argument if you want, but I'm just going to reference the proof here. And then, so that means that this is just x. So Bnf of x is just x, actually, for every n. So it's actually just the same as f itself. So that's kind of, I don't know, kind of interesting. Let's do the other one. So Bnf of x, if f of x is x squared. So this time we would get k over n squared. I'm going to avoid writing the indices now just for convenience. So then we'd have n over k. And then we have x to the k, 1 minus x to the n minus k, right? So this one, so this is like 1 over n squared, k squared, then choose k, x to the k, 1 minus x to the n minus k. And if you look at the proof of 27.2 again, they do something that's like almost exactly the same as this here, except instead of k squared, they have k times k minus 1. But because we already computed, so from here, let's do it this way. So from 27.2, we have that the sum of k times k minus 1, and choose k, x to the k, 1 minus x to the n minus k. This equals n times n minus 1 x squared. But on the other hand, this also equals like the sum of k squared, and choose k, x to the k, 1 minus x to the n minus k, minus the sum of k, and choose k, x to the k, 1 minus x to the n minus k, right? So this is, oh yeah, okay, I think this works. Yeah, so this is what we're interested in. So what we have is that this is like 1 over n squared times this plus this, right? If you like add this term to both sides. But this here is, we already computed that. That's just n times x, right? So it's like n times n minus 1 x squared plus nx, right? So this is n minus 1 over n x squared plus x over n. All right. So this one, it's not actually exactly equal to x squared, but you can see that it converges to x squared. At least point-wise, it's obvious that it converges to x squared because this goes to 1 and this goes to 0. So yeah. Any questions about that? Okay. Well, how about in general? I mean, do you have any questions in general about the material so far?
I had some questions on the midterm, if that's okay.
Yeah, sure.
So for the last one, for problem 9,
Mm-hmm.
I was just like, I see why the 1 over log k works, but
Yeah.
I don't know like what the motivation was. Like, how did you get there? I guess.
My thinking was like, actually, you know what? Now that I think about it, you could also just use like 1 over square root of k. Basically, my thinking was like this. This is a good question, actually. I'm glad I have an opportunity to explain this. Because, yeah, I don't know. It's hard to like type up these kinds of things. But basically, in my head, I was thinking like, okay, so um, so we want the the like either the even number terms, right? Like one of the two types of terms, we want them to like be a little bit imbalanced, right? So we want there to be a little bit of like residue. So if you think about it, it's kind of like the even number terms and the odd number terms are kind of, they're like fighting against each other, right? And it's like, I don't know, you can kind of think of like each even numbered term kind of cancels out some of like the previous odd numbered term or something like that. And so if the if the how am I trying to explain this? Like, yeah, if the absolute values of the terms are not required to like all strictly, decrease basically, or not strictly, but like they don't have to form a decreasing sequence, then like each odd numbered term can kind of be a little bit bigger in absolute value than than like the next even numbered term basically. So it's like that would be one, that's kind of like one approach to trying to sort of like imbalance them. So it's kind of like we want the odd numbered terms to be a little bit bigger in magnitude, right? And then the idea is that it's like the excess in the odd numbered terms should be should form a divergent series with terms approaching 0, right? So the idea is that it's like, so like one, like the obvious choice, right? The obvious choice of a divergent series whose terms approach 0 is like the harmonic series, right? So say we want like we want like each odd numbered term, you know, plus like the next even numbered term to be 1 over n, something like that, right? Or like, or 1 over k or whatever, right? So like sort of like the kth odd number term plus the kth even number term should be like 1 over k or something like that. Then if you think about it that way, right, then the idea is basically that like we can make like an plus 1 over an go to 0 as long as like 1 over k is like small compared to the values of an plus 1 and an. Okay, where like k, you know, k is approximately like n over 2 or whatever, right? Depending on whether n is even or odd, k could be like the floor of n over 2 or it could be equal to n over 2 or something like that, right? Or yeah, the ceiling of n over 2, I guess, but whatever. So the point is like k is approximately 1/2 of n. Yeah, so and the thing is, it's like, okay, so we want like an to be like something plus 1 over k, where like I guess like a 2k minus 1 for the odd ones to be something plus 1 over k, where something goes to 0 but like is slower than 1 over k, so that something, this dot dot dot, still dominates, you know, the overall value, right? So that like this is going to 0, because we obviously need these terms to actually approach 0 to satisfy the requirements of the problem, right? But the point is that like no matter what, like if we chose this, you know, this kind of residue here that we're using to form like a divergent series, you can always find another like sequence that approaches 0 much slower than this one. And any sequence that approaches 0 slower than this, you can use that to form kind of like the dominant piece of the expression here. And then like a2k can be like negative of this thing, right? To just like cancel that out. So it sort of doesn't end up mattering in the long run, because you end up accumulating, you just end up like accumulating all of these 1 over k terms and getting this like larger and larger positive value. Even though like 1 over k is actually a very small, you know, small relative to like the overall values of a2k minus 1 and a2k, I guess. Yeah. Does that help?
Yeah, I mean, I guess like the additional condition of like the an plus 1 over an, like so that goes to, or I think that goes to 1, but
Oh,
like
sorry, yeah, that's what
yeah,
yeah.
but like so that has to go to 1 like even slower, I guess, than the partial, because like I got confused because they like I thought that as the limit approaches 1, that like the difference between two terms has to keep getting smaller and smaller, and so I
That's
didn't
true, yeah.
know, like yeah.
Yeah, I think if you look at what you end up getting for these expressions here, like in the case of the log of k, 1 over log k and 1 over k thing, or even, I mean, pretty much no matter what you do, I think you're right in some sense that these end up converging to 1 slower than like the somehow, like I don't know how to quantify it like immediate off the top of my head, but yeah, these do go to 1 like very slowly. I think slower than these like go to 0 or something. Yeah, slower than the differences go to 0, something like that, I think. because you end up getting something like, 1 over like 1 plus log k over k. So you have this kind of like log k over k thing, which obviously that approaches 0 slower than 1 over k itself approaches 0, right? And then in the other quotient, you have like log k minus 1 over log k plus like log of k minus 1 over k or something, I think. Yeah. And so both of these things, like this approaches 1 very slowly, or actually, sorry, this approaches 1 rather quickly, I think. But this approaches 0 very slow, or like slower than 1 over k. Yeah. Slower than 1 over k. I'm not sure if that's what you were getting at, but yeah. Yeah, it's like I think so. Like the point of this problem was not just to be like tricky and annoying and hard, but rather to like really emphasize exactly how delicate alternating series are. Like I don't know. I think it's like easy for people to kind of like relax the conditions of like the alternating series test in their head and assume that this like a series with these like relaxed conditions should still converge, even though like actually you can develop these like weird series that are like almost alternating series, but they're just slightly off. There's like just this tiny little imbalance, right? Like there's a very, very slight imbalance between the positive and the negative terms that actually causes the series to end up diverging. Like that's, I don't know. To me, that's like it's a slightly surprising fact, I guess. And it's like, I don't know. It seems subtle, but I think it's kind of important, I guess. Yeah. Any other questions about the midterm or otherwise? Yeah, I was pretty broken up over that problem 7 thing. I really did not notice that until I started writing the solutions earlier today. That the problem ended up being like literally trivial, just because I just get into this habit. I have this like very bad habit of just like calling every function continuous for some reason. Even like it's so rare. The problem is like it's actually so rare that you prove anything about functions, like generic functions. I mean, you almost never prove anything about like generic functions in analysis. So you get in a habit of just like putting adjectives in front of a function when they maybe shouldn't be there, I guess. So yeah, it wasn't supposed to be continuous in that problem. So yeah, I hope you read the solution for that, because I think that's actually also like, in my opinion, that problem in its proper form is actually educational. Like I kind of try to design the problems on the test not just to be like challenging and to be like hard to cheat on and to be creative and stuff like that, but also like I think at least a decent number of them are supposed to like have a sort of a lesson in them. Not all of them, obviously, but a lot of them, I think I intend for them to like carry some kind of a lesson. And so problem 7 definitely is like it's a fact that's like worth being acquainted with in its own right, not just as a problem on a midterm, but like a general fact about monotonic functions, that the limits, one-sided limits from both directions exist for increasing or decreasing functions. I guess on an interval. So yeah, anyway, let's see. Let's do another problem. So I like this problem. Yeah. So show if f is continuous on R, there is a single sequence of polynomials Pn such that Pn approaches f uniformly on any bounded subset of R. So there's a hint here. Arrange for f of x minus Pn of x less than 1 over n on negative n. Yeah. So yeah, let's take maybe 10 minutes. So let's resume, or like resume at 5:50. And I'll make a little room here. Oh. Okay, hold on. There we go. All right. All right, so let's see. So the hint, right? The hint tells us that we should try to, argue that we can construct our sequence so that this is true, right? So why would that be the case? So basically the question is, right? Okay. Why can we always choose Pn such that f minus Pn is less than 1 over n on negative n. Why is that? Would you guys like to venture? Well, if we fix n, right, then, the Weierstrass approximation theorem tells us there exists a sequence of polynomials uniformly converging to f on negative n, right? So there are sort of like different sequences potentially. There are potentially different sequences for each n, right? For these different intervals, basically. But the point is that you can pick one polynomial out of each one of those sequences, right? So we can pick Pn to be one of these for which f minus Pn is less than 1 over n on negative n, right? Like if you call like say Qn is the sequence, well, let's not use n, Qk converging uniformly to f on negative n, then there exists some k such that for k greater than k, absolute value of f minus qk is less than 1 over n on negative n. So take Pn equals, qk for some k greater than capital K, right? So pretty much, yeah, I mean, yeah, who knows where in the sequence it actually happens, but eventually somewhere in this sequence of polynomials, there's a polynomial that's uniformly within 1 over n away from f on this entire interval, right? So, okay, I'm just going to erase this. So you can pick Pn to be that polynomial. And then once you have that, those Pn's form a sequence. So we claim Pn converges to f uniformly on any bounded subset of R. Say S is bounded, then S is a subset of negative capital N for some capital N, right? So then well, actually, I guess call this like N1 or something. Pick N greater than N1 such that 1 over N is less than epsilon. Like if we're given epsilon So yeah, if we like let epsilon be greater than 0 over here, right, then yeah, we can pick capital N this way. So then Pn minus f is less than epsilon for all n greater than this capital N, right? Because by the way we chose Pn, this is because Pn minus f is less than 1 over n, which is less than epsilon on negative n, and s is a subset of negative n for all n greater than n, because s is a subset of negative n1, which is a subset of negative n, which is a subset of negative n, right? So, so yeah, this inequality holds on the given set S. So Pn goes to F uniformly on S, right? And that's true for, so S was an arbitrary bounded subset of R. So yeah, there you go. Any questions? All right. Well, in that case, I think that's it for today. So yeah, you know, I have office hours tomorrow, and then after that, I'll see you guys next week.
Thank you.
Mm-hmm.
Thank you. Bye.
Bye-bye.